All right, first question, the box is released from rest on top of a frictionless ramp. I want to calculate the velocity that it leaves the ramp with, so I'm looking for this velocity right here. And I want to leave my answers in terms of the heights and constants. So from here to here, a frictionless ramp, we're going to use energy conservation. I am starting with potential energy. It's starting from rest. This is only potential energy. We need to decide what we're making our zero or ground level. If you want to make this your ground level, so I'll mark it like this, that's totally fine because I'm just going from this point to this point. So that would be going from all potential to all kinetic. So that would be potential at this point equals kinetic at the bottom of the ramp. Potential would be mgh equals kinetic 1/2 mv squared. The mass is going to cancel out. To get rid of the half, I'm going to multiply everything by 2. So 2gh equals v squared. So then the velocity is square root of 2gh. Now, if you did not like this as your ground level, that's fine. We can use the literal ground level that it said. In that case, I would have kinetic and I would have potential here. And that means that this potential energy has a height of h and this h right here. So this would be like an mg height of little h plus big H equals 1/2 mv squared plus mg big H. If this is the case, when I subtract the mg big H over, then see how your mg big H term right here is going to go away? So then you would just be left with mgh equals 1/2 mv squared, which is going to get you the same answer here. Now, conceptually, if you think about it, right, the height of the ramp absolutely matters. Whether I place this ramp up here or down here, it shouldn't matter because it's going to come off the ramp with the same speed no matter how high the table is. B is asking to still calculate the velocity it leaves the ramp with, so I'm still looking for V, but now I'm looking for my answer in terms of D and H in constant. So I'm looking at this part right here with the D and the capital H. This is not energy conservation because I can't use like the x distance versus y distance with energy. Energy doesn't tell direction. This is a projectile question. So I've got my x distance, right? Delta x is going to be d. Delta y is going to be h. I'm looking for the x velocity. That's my unknown. I know my initial velocity for the y direction is 0 because it's shot horizontally, not up or down. And I know the acceleration in the y direction is g. Like I said, we're looking for the x velocity. X velocity, I'm going to use just v equals c over t. That means I need to find time, so I'm going to use y to find time. If you look at your equation sheet, the equation that has time and also the displacement is the delta x equals v naught t plus 1/2 at squared. Now it's tempting, because this says delta x, to use the distance, but this equation, I'm actually not using x values, right? I'm using y values, so I'm going to call that delta y instead, because I'm using g, which is in the y direction. I'm using the initial velocity for y, so all these to be y values. So my change in y is capital H, v naught is 0, 1/2 gt squared. To get t by itself, I'm going to multiply this t up. Now I'm going to divide by g, and lastly I'm going to take the square root, so time is the square root of 2 capital H over g, and then the velocity would be v equals d over t. D is literally distance d, and time is what we just calculated it to be. And it should make sense that this velocity is this distance over this time, and the time depends on this height right here, because we're just talking about the time that it's falling down in the air, not from the start to the finish, just from here to here. If I want to increase the distance, would I increase or decrease h? Now some of you are looking here and you're like, little h isn't in the equation. So think about it. First of all, let's get d by itself because we're looking what the effect on d would be. So d would be v square root of 2h over g. Now, you can't just say v or d does not depend on little h, because when you look at this, yeah, I don't see little h in the equation, but I do see velocity. And the velocity that it comes off the ramp with will depend on this height right here. So the qualitative versus quantitative, I started with qualitative. If we look at this, if I make this a super tall ramp, right, that is not going to land at the same spot, because now that I've increased the height, I am increasing the potential energy, which is then coming down with more kinetic, which means it's coming out faster, which will then go farther. So the qualitative would be if you increase so increase little h, because you will start with more potential energy at the top. So you will have more kinetic energy coming off the ramp, which means that it comes off faster, which means it'll go farther horizontally, which is a greater distance, d, horizontally. And your quantitative is, we calculated the speed that it comes off with is v is the square root of 2h. So as h increases, the velocity will increase. So the distance will increase too, because v equals, or I'll just say d equals vt. So if your velocity increases, then if your height increases, your velocity increases. If your velocity increases, your distance will increase. If you want to increase distance, what would you do to the height? So here, right, the capital H isn't going to make it come off any faster. I'm still going to come off at the same speed, but now if I increase this capital H, then I'm going to be increasing the time in the air. So you would want to increase capital H because you still come off with the same velocity, but you are in the air for a greater time, so it goes farther. Again, you can use the d equals v times t, right? If I keep the same velocity but I increase the time, that would increase the distance. You can also rearrange d is v square root of 2h over g. So as h increases, d will increase as well. That's your quantitative part. But the conceptual part is important to understand. I might come off with the exact same speed, but if I'm going the same speed, but I do it for a longer amount of time, then I will go farther. And increasing the height will increase the amount of time that it's in the air. Alright, A and B, they both have a mass m and an initial velocity v naught, and it's on a rough track. Rough meaning that there is friction, meaning that energy is not conserved because there is work being done. So here, if energy was conserved, they'd go to the same height because they start with the same potential, same kinetic energy, they'll go to the same potential. But energy is not conserved. They're both experiencing work due to friction because I do have this coefficient of friction. That tells me that, right, they're losing energy. If you look, B is not traveling as much as A would be on this track. So because A is traveling a greater distance, it's going to experience a greater amount of work. B doesn't travel as far, so it's not going to have as much work. So I'm going to say box B has less work done by friction because it has less distance traveled. So because it has less work done, that means it doesn't lose as much energy to friction. So it has more potential energy, so it goes higher. So box B will go higher. Now you also could have said box A travels farther, therefore has more work done, loses more energy, has less potential, so does not go as high. Same thing, just the flip, the reverse. Alright, we want to not come up with like an equation. We want to just conceptually answer this one. So we have two carts, and I know that cart A is going to have the faster velocity because it literally tells me, explain why cart A has the faster velocity. So it's kind of giving you the answer. You just have to justify it. Now the tempting part here is people go, oh, it's higher, so it has more potential, so it has more kinetic, so it goes faster. That's actually not true. Yes, it is higher, but it does not hold any more potential energy. This one has twice the height, which normally would be twice the potential energy, but this one has twice the mass. Think about potential energy is mgh, right? For cart A, it's got mg2h. For cart B, it's got 2mgh. Either way, this is a factor of 2 times mg and h. It's the same amount. So both carts start with the same potential energy because 2H and 2M, right? Cart A has 2H, but cart M has 2 masses. So that's going to be starting with the same potential energy. Now, that means that because energy is conserved, right, they're going to have the same kinetic energy at the bottom. So they both have same kinetic energy at the bottom. Now, normally you would say, okay, if they have the same amount of kinetic energy, then they should have the same velocity. But think about, if kinetic energy equals 1/2 mv squared, just because KE is the same does not mean their velocities are the same. KE also depends on mass. Here, because they have the same KE, but they have different masses, that must mean they have different velocities. The one that has the faster velocity is the one that has the smaller mass, right? Because if this increased, this would decrease to still keep the same kinetic energy. So because they have the same kinetic energy at the bottom, but this one has less mass, it must have more velocity. So cart A has the same KE, but less mass. That means it must have a greater velocity then. Right? This one has the equal amount of KE, but it has more mass. That means the velocity must be less. Here we've got 2 slides. The same ball is released from rest. Assume friction is negligible, so energy will be conserved here. Which one will the ball be moving fastest at the end? So let's label it in 1 and 2. So it will be moving at the fastest on slide 1. Because, so 2 ways to think about this. You can think about the change in energy. So I said slide 1 has the greater change in potential because it has a greater change in potential energy because it loses more height. A greater change in potential is going to mean a greater gain in kinetic. I'm talking about the exact same ball, so that gain in kinetic didn't have anything to do with the mass. It had to do with more velocity. So greater gain in kinetic is going to mean a faster velocity. The other way to think about this is like sharing the energy. So they both start with the same total energy, but in for slide 2, it has to share some of its starting potential with potential here. So not all of it went to kinetic. So I didn't write this one down, but we can say slide 1, all the starting potential goes to kinetic. For slide 2, only some potential goes to kinetic, so it's not as fast. Alright, now we want to actually derive an equation for the velocity in slide 1 and slide 2. Here, it's starting from rest, so I'm going mgh into just mv, 1/2 mv squared. M's canceled, 2gh equals velocity square root. Here, I'm starting with mg capital H, and then it's going to mg little h and 1/2 mv squared. M's still cancel. Subtract this little h over 1/2 v squared. Multiply everything by 2. Take the square root. 2 times g capital H minus g little h equals your velocity. And this is consistent, right? We said that this one would be faster. See how this velocity is this velocity minus something, so that means it must be less than this one if you're taking away from it. All right, on a frictionless ramp, which object will reach the ground with a greater velocity? So frictionless means that energy is conserved. They're all starting at the same height. They're all ending at the same height. So because they all started at the same and ended at the same, they've changed by the same amount of potential, which means they've gained the same amount of kinetic. So then they will have the same speed. Here, I would say they all start with the same height. It's the same object, so it's the same mass, which means the same potential energy. So we'll have the same kinetic energy at the end. So I'll have the same velocity at the end, regardless of path. Right? No matter what path it takes, right? You could think about like If energy is conserved, it doesn't matter how many times you go up and down, at the bottom your velocity is going to be the same as if you just went like this, as long as energy is conserved, as long as it's frictionless. Now, which one reaches the ground first? That's different. They do have to have the same velocity at the very, very end, but they don't have to have the same velocity at every single point, right? Just when their heights have changed an equal amount. This one is steeper, so it's getting its velocity very quickly, whereas this one goes slowly and then speeds up. This one is slowly speeding up or steadily speeding up the whole time. So I would say slide 1 is definitely the one that reaches the ground first because it has a faster average speed. So on average, its speed is greater, even though they end up with the exact same speed at the very, very end. And the reason, right, you can't just say it has a faster average speed. The reason it has a faster average speed is because it is steeper at the beginning or at the start. So it reaches its fastest speed earlier than the other slides. Right? If I know this is going to have a speed of, I don't know, 5 meters per second at the end, see how they reach the 5 meters per second early on? This one takes the entire time to reach it. This one's going slow, and then at the very end gets to the 5 meters per second. So even though they all end at 5 meters per second, this one was faster on average. Alright, that was the typo. It was supposed to be, it just starts with initial velocity vi at this point, and I'm trying to find the velocity at A. So here you have both potential and kinetic. At point A, you still have potential and you still have some kinetic. I have less potential and therefore more kinetic. So I'm going to start with mgh plus 1/2 mvi squared, that's the beginning, goes to, here I have mgh over 2 plus 1/2 mv, I'm going to call it va squared because we're going to have multiple velocities. This is, I'm looking for the velocity at point A. M cancels out. Most people like to get rid of the halves, so I'm going to multiply everything by 2. That cancels out the halves here. It cancels out this 2, right? 2 over 2 cancels out, and now I have a factor of 2 right there. So I now have 2gh plus vi squared equals, this is now gh plus va squared. Subtract the gh over. 2gh minus gh is just 1gh plus vi squared equals va squared. So then now we just take the square root. We cannot say, oh, square root of square canceled, because this is, I'm going to keep it inside of the square root because it's being added. It's not being multiplied, so I can't separate them. So just leave it like this. Now I want to find the velocity at point B. At point B, it would be all kinetic energy. So I'm going to still start with this, like this point to this point. You can use A, but then you're going to have to plug in the velocity at A into your equation, and it's going to get me the same answer as the starting energy here. So I just go back to the beginning, which is mgh plus 1/2 mvi squared. And that's going to equal my kinetic at B, which is 1/2 mvb squared. M still cancel out, multiply by 2, that's 2gh plus vi squared equals vb squared. So then just take the square root to get vb. Square root of 2gh plus vi squared. Now, you'll notice that the velocity at B is bigger, right? A factor of 2 added right here instead of just the 2h, or sorry, instead of just the vh, and it makes sense that it's faster here because I lost more potential, meaning I gained more kinetic. C, I want to know how high it will reach on the next hill before it falls back down. Before it falls back down, that would be velocity of 0, which means kinetic energy would be 0, which means you have all potential energy. So I want to end with just mgh, and not this h right here, but some h that I don't know. You can call it capital H, right? Either, it doesn't matter what you call it. You can call it h at the end. That's like, but it's, I would call it something other than this because it's not the same height, right? I'm looking for what this is. And then, so looking for the energy or potential here to get the height right here. Well, you could compare it to here, but then you'd have to plug in your velocity at B to your equation. So I'm just going to go back to the energy at the beginning because either way it's being conserved. So we've got mgh plus 1/2 mvi squared. M's cancel, and then to get this h by itself, you just divide by g. You can leave it like this. Some people said G over G, cross out. Okay, you can cross it out for this term, but it's still over G here. That would be the same as H plus VI squared over 2G. 1/2 is the same as dividing by 2. You can leave it like this or rewrite it like this. It doesn't matter. What you'll notice is that the ending height, the max height that it can go to, is greater than this initial height, right? Little like H plus something else. And that's reasonable, right? Because I had a velocity here. So then if I'm going to until you can't move anymore, it would go higher than when you did have a velocity. A box of mass M is released from rest at point A, long frictionless. This is the height H. From D to E, you do have friction, just in here though. And we're trying to find the speed at point D. From here to here, it's frictionless, so energy is conserved. So I'm going to say energy at A equals the energy at D. Energy at A, it says starts from rest, so that's just potential. Here I have some potential and some kinetic. So that's going to be mgh plus equals mg. This height is the height of z, plus 1/2 mv squared. Take out the m's. This is going to be gh minus gz equals 1/2 v squared. Multiply everything by 2, so I'm just going to put it in parentheses. Take the square root, 2gh minus 2gz. You can distribute the 2, or you can multiply or keep it in parentheses. It doesn't matter. They will be equivalent. And yeah, okay, cool. And this should make sense because, right, if I were to increase this height, then that would increase the velocity. If I were to increase z, you'd be taking more away. That would decrease the velocity, which makes sense, right? Because all I care about for the kinetic energy is how much the height changed by. So it changed by h minus z. B, determine the value of d so that the box comes to rest at point E. So from here to here, right, we're obviously doing work because from here to here, if it comes to rest, right, it's losing kinetic energy, and it's not like it went into potential because the height didn't change, it's level. So I'm going to use work, which tells me that the change in energy equals Fd. Specifically, the force that's doing the work is the friction force, so that's going to be mu Fn. In this case, right, Fn is just going to be equal to your mg. So mu mgd gives me my work done, and that is also equal to my change in energy. Think about, from here to here, my potential energy is not changing. Only my kinetic energy is changing. So I'm going from 1/2 m, the velocity was 2gh minus 2gz in the square root squared, to 0. So when you square the square root, that cancels out. The half cancels out the 2, and then we have mgh minus mgz. And that's going to 0, so when you do the change, you get 0 minus mgh plus mgz when you subtract, right, negative, negative. Or you can think about it as like this, but then that's going to go away, and you're going to get this. I don't know why I did that. Okay, equals, technically this would be negative, so anyway, we're going to divide the mg over. You'll notice that the m and the g's cancel, so I've got a negative h plus z equals negative mu d. So when I divide that, it's going to switch, so you've got z minus h over mu. Oh, I like this. Let me fix this.